Greetings! Welcome to Electronic Circuits 1. I am Razavi and this is lecture number 45. This is my last lecture in this Electronic Circuits 1 series. Today we will continue to look at op-amp imperfections and see how they influence the performance of circuits that use op-amps. First, let's look at what we covered last time. In terms of some of these effects, we started by looking at two other circuits that use op-amps. These are nonlinear circuits. We saw that we can build a precision rectifier, meaning a circuit that can rectify an input even though the input might be only a little above zero, only a small positive value, as opposed to a single diode where we would have to exceed 800 millivolts approximately before the diode turns on and performs rectification. So we saw that by placing a diode around an op-amp from the output to the inverting input, we can create this type of characteristic. So even for very small positive values, Vout follows the input, this output follows the input, so that is passing the signal. And then for even small negative input, the diode turns off and there's no current through this resistance, so the output is zero. Another type of circuit is a logarithmic amplifier, log amp, that has a characteristic from the input to the output that looks like a log function. And to do this, we place a bipolar transistor in the feedback loop from the output back to the input. And again, we saw that this circuit has this type of characteristic. Then we talked about op-amp non-idealities, and we saw that one important non-ideality is the offset voltage. And what that means is that when we plot the input of the op-amp as a function of the output of the op-amp as a function of the input, we see that even though in the ideal case it crosses zero, crosses the origin, in actuality it doesn't. It's shifted to the right or to the left, or equivalently shifted down or shifted up. And the point on the horizontal axis where the output crosses zero is called the offset voltage. And we modeled that by a voltage source in series with one of the inputs. We said that VOS is a random quantity, so it has different values and different polarities, positive and negative. So as far as the polarity is concerned, we can put it here or we can put it here. It doesn't make any difference. Okay, so today we will look at the effect of this offset on the performance of integrators. And in fact, if you remember when we studied integrators, I said the integrator circuit I showed you would not work in the lab. And that's exactly because of the problem of DC offsets. So that's what we will do. And then we'll look at some other imperfections of op-amps, such as the input bias currents and the finite speed. All right, so let's talk about the effect of DC offsets on integrators. We draw an integrator and we insert a DC offset at the inverting or non-inverting input of the op-amp and then see what happens. All right, so here's our integrator, R1 here, C1 here, and the input ordinarily goes here. The output is taken from here, and I need to insert a DC offset. Maybe I will insert it here. So I insert a DC offset here, VOS, and I would like to see what the circuit does in the presence of this VOS. Okay, all right, maybe actually what we will do is we'll set the input to zero. In a sense, we're using superposition, and just see what the circuit does in the presence of the offset. So let's set this to zero and analyze the circuit just with an offset. Okay, well, for these types of studies, we assume the op-amp has a very high gain. So we can assume that these two voltages are very close to each other. And now we need to find the output in terms of VOS. Now VOS is a constant voltage. So the transfer function from here to here is not very meaningful. VOS is constant, right? So we should look at something else. Maybe we should look at the time response of the output when there is an offset here and see if it does something interesting and perhaps troublesome. Okay, so then I start out by saying that C1 has a zero initial condition on it, no charge, no voltage. We have a constant voltage here from the non-inverting input to 0, and we would like to find an expression for V out as a function of time. Does the output change with time or not? We don't know, maybe, so let's pursue that. Okay, so to do this, we will write this voltage as approximately equal to the offset voltage. We know that, right? Because the gain of the op-amp is high. So as I said before, from this fundamental equation, if A0 is very large and V out, this whole thing is a moderate amount, V in 1 and V in 2 have to be very close to each other. So these two have to be very close to each other. We can say this is also approximately equal to VOS. Okay, so now let's go ahead and see what happens. If this voltage is VOS, I know the current through R1 flowing this way. R1 has 0 on its left terminal, VOS on its right terminal. So the current through R1 is just VOS over R1. Okay, that's easy. And this current must flow through C1 because it has nowhere else to go. So the current through C1 flowing this way is also VOS over R1. All right. Now if I have a current through a capacitor, I can find its voltage. What we know is that the voltage on a capacitor is equal to C dV over dt. The current through a capacitor is equal to C dV over dt. So the voltage on a capacitor is 1 over C integral of I dt. Okay, so the voltage on the capacitor, which happens to be equal to V out minus VOS, that's the voltage difference from here to here. So V out minus VOS is equal to 1 over C integral of I dt. I, the current of the capacitor, is VOS over R1. So VOS over R1 is C1 dt. Okay, we do have to be careful with the polarities here. The current is going this way, so we have to pick this voltage minus this voltage and use that in these expressions. Okay, so because VOS and R1 are constant, this reduces to V out is equal to VOS plus 1 over R1 C1 T. So this looks like this, right? It starts out V out as a function of time. At time 0 it's equal to VOS, so it's right here. And that makes sense because if the capacitor has no charge on it at time 0, it has 0 voltage difference from here to here. And because this voltage is already VOS, this voltage has to be VOS as well. So that's why we have VOS here. So the output starts at VOS and then takes off and rises linearly. Oops, I messed up this drawing a little. So the output starts from VOS and then rises linearly. Okay, but how far will this go? Well, this will go on until the op-amp just cannot produce a higher voltage, meaning that when this voltage hits the supply voltage of the op-amp or close to it, then that's where we stop. So it goes and eventually gets stuck somewhere. This would be near the supply voltage, maybe lower, but somewhere around there. And that's what happens after you construct the integrator in the lab. So at this point, the output of the op-amp has hit the rail, the supply rail, and has saturated. So the op-amp is essentially dead. Now, if I come along and I apply my input, the op-amp is dead, there's no gain. The gain from year to year is close to 0. The circuit is not an integrator. We have nothing. So we say that the integrator has integrated the DC offset of the op amp and reached saturation. And that's why this integrator does not work if you build in the lab, because it is very unlikely that you can buy an op amp with 0 offset voltage. So any amount of offset that we have here, 1 millivolt, 0.1 millivolt, 1 microvolt, doesn't matter, will eventually give rise to this effect. So that's the problem. Sorry, there's a V offset here that I forgot in this expression. So it integrates its own offset and saturates. Okay, so that's the problem with this type of integrator, and we have to find a fix for it. You see that in this case, it's really just a functionality question. When we saw the effect of offset in the previous circuits, the inverting and non-inverting amplifiers, we had some amount of error at the output, the amplified offset. But here it's detrimental. It's just not an error, it's just dead. The circuit has died because of the saturation effect. So we really have to fix it. Okay, so to fix the integrator so that the offset does not saturate it, we will play a game. So that's what we will do. So to fix the circuit, we take the integrators as before, R1, C1, and of course there's an offset here. I can draw that offset as well. We know that there's an offset in the op amp all the time. And this is our input. And what we do is we add a resistor in parallel with C1. So let's call that R2. And I claim that R2 does not allow the offset to be integrated indefinitely. It doesn't allow the offset to be integrated. So let's see how that's possible. Okay, well, maybe the best way to think about this is to go to time infinity and see what happened. At time infinity, we are hoping that this capacitor will have no current through it if all the transients have died away. All right, so what exactly happens? If I consider the previous case, I still have an offset here. Let's say the input is 0, which means I still have VOS here, which means I still have a current of VOS over R1 through R1. Now previously that current had to flow through C1, and the voltage across C1 grew and grew and grew, and that's what we got. But here the current through R1 doesn't have to flow through C1, at least at time infinity. It can flow through R2. So if it flows through R2, it generates a voltage, but that voltage does not grow with time. It's just a constant amount. So the output will have a constant error in it, but not something that grows with time and saturates the op amp. Okay, so the intuitive explanation is that in the presence of an offset, this R1 needs to have a current like before, but that current prefers to flow through the resistor, not through the capacitor, if we wait long enough, because all the transients die away. Okay, so in that case, we can find out what the output is if Vin is 0. So let's say, so I'll write it here, if Vin is 0, then what we have is this. After all the transients have died away, C1 is an open circuit, and VOS sees an amplifier from here to here, which is a non-inverting amplifier, because we took the output, we went through a resistive divider, and we went to 0. So the output is simply equal to the amplified copy of VOS. VOS is amplified by 1 plus R2 over R1, just like an ordinary non-inverting amplifier. So it's equal to 1 plus R2 over R1 times VOS. So yes, we do have some error at the output, this much. This much DC is sitting at the output, riding on top of anything that's coming through the circuit. So when we apply our input, the input goes through the circuit, generates an output, but in addition to that, we have this DC that's sitting there. All right, so, but what's important to remember is that VOS over R1 prefers to flow through R2 rather than through C1 at t equals infinity. So the voltage agnostic capacitor does not grow indefinitely. The op amp does not saturate. The op amp only produces this much offset. So if R2 over R1 is, let's say, 10, we amplify the offset by a factor of 11. If the offset is 1 millivolt, we have 10, 11 millivolts, 15 millivolts, 20 millivolts of offset at the output, which is not a huge deal as opposed to when the op amp saturated completely. Okay, so that is the fix. But now you might ask, is this circuit still an integrator now that we have a resistor in parallel with C1? Did we change the nature of the circuit? Does the circuit have any resemblance to the integration that we saw before? All right, well, let's analyze the circuit in the frequency domain, find this transfer function from V in to V out, and compare that to what we got here, and see if there's any resemblance to integration. If you remember the ideal integrator transfer function, so let me write this here. So the ideal integrator transfer function, as we found it last time, was a function with one pole at the origin. So it was equal to minus 1 over R1 C1S. Right? That's what we found last time. So now we will find the transfer function of this new circuit and see how close it can be to that ideal transfer function. Now when we are trying to find the transfer functions, of course we're dealing with small signal analysis. This VOS is set to 0. So I need to find the transfer function of this circuit. So let me write, so actual or the new integrator. So here's what we have. We have an R1 connected to the input, and then we have a capacitor C1, a resistor R2 going to the output, and we would like to find the transfer function of this circuit. Again, as usual, we try to see if this circuit resembles anything we have studied in the past, so that we don't have to write KVLs and KCLs from scratch. And indeed, this circuit resembles the general circuit I showed you last time. We called it the general inverting circuit, where this was called Z2, what goes from the output to the input, and this was called Z1. And we saw that V out over V in, if the gain of the op amp is high, is approximately equal to minus Z2 over Z1. So we just have to find the impedance of a resistor in parallel with a capacitor. And that's just this, R2 over R2 C1S plus 1. And then divided by Z1, which is R1. And this gives us minus R2 over R1 times R2 C1S plus 1. So that is the transfer function of the new circuit. It doesn't quite look like an integrator, but not all hope is lost. If you look at it carefully, we can identify a special case, and the special case is as follows. If R2 C1S is much greater than 1, then we have this R2 cancel this R2, and we end up with minus 1 over R1 C1S, just like before. So for this circuit to be a good integrator, we would like that to happen. So to be a good integrator, the circuit requires that R2C1S be much greater than 1. Now the problem is that S generally is a complex number. So I cannot say a complex number is much greater than 1. So what we do is we say the magnitude of R2C1S is much greater than 1. All right, so what does this mean? Well, this means that, of course, we have R2 and C1 under our control. But it's really S that plays a role here. S is the frequency of the input. So if I apply like a sinusoid at the input, then the frequency would be j omega, and that's what's going through. So in other words, this circuit is a good integrator so long as the frequency of the input, omega, times C1 times R2 is much greater than 1. So for frequencies that are sufficiently large, the circuit is a good integrator because it satisfies this condition. But if the frequencies are very low, it's not a good integrator. So for sufficiently high frequencies, it's a good integrator. Okay, so omega, the frequency of the incoming signal, has to be large enough so that this condition holds. Actually, intuitively, we can see why the circuit is not a good integrator if the input frequency is very low. Let's say the input frequency is very, very low. Then what happens? Well, if the input the input frequency is very, very low, this capacitor is an open circuit. We know that at very low frequencies, the capacitor has a very high impedance. It's like an open circuit. If that's an open circuit, what do we have from here to here? We just have a non-inverting amplifier. We don't have an integrator anymore. Right? We have an inverting amplifier. We don't have an integrator anymore. And that's why the frequency has to be high enough so that this capacitor dominates this impedance, meaning that this impedance is approximately equal to the impedance of the capacitor. And that means that the impedance of the capacitor must be much less than R2. And if that's the case, this is the condition, and then we have a good integrator. So this fix that we apply to avoid this saturation problem does limit the frequencies that the input can have while we are performing good integration. But that's the price that we pay. We can pick R2 to be larger and larger for this to be satisfied. But if we pick R2 to be larger and larger, then the offset is also amplified by a larger and larger amount. So we have to balance these things. All right, so that is the integrator and the way we fix the problem of the offset. Let's go to another interesting imperfection in op-amps, which we call input bias currents. This happens in bipolar op-amps because if you remember, bipolar transistors have a finite base current because the beta is not infinity. So we have a collector current divided by beta, we have a certain base current. And the inputs of the op-amp, if they are connected to bipolar transistors, will have a certain amount of current in here and here, which is drawn by the circuitry inside. If you remember, when we looked at the 741 briefly, we had something like this. We had a transistor like this, which looked like an emitter follower, and then something like this, which looked like a common base stage, and similarly on the other side. So those are the circuits that we had before. And what we expect is that there is a base current drawn by this device and drawn by this device. So these are the currents that are drawn here. Okay, so if we buy a bipolar op-amp like the 741, then we do need to remember that the inputs need some sort of bias current. That bias current has to come from somewhere. Right? This guy needs a bias current, has to come from somewhere. If it's an open circuit, the bias current is not there, the device is not biased, everything is dead. You don't have an op-amp. Okay, so first, how do we model these bias currents? Well, it's very simple. Assuming that these currents are constant, we just model them by constant current sources. So we attach a constant current source from here to ground, call it IB1 for example, and another one from here to ground, call it IB2. And these are the two inputs of the op-amp. In other words, the op-amp consists of the sort of the ideal op-amp, or the op-amp that we have studied before, and two additional current sources that model these currents. To find the value of these currents, we go to the data sheet of 741 and see how much they are. I don't remember, maybe a microamp or 0.1 microamp or something in that range. So those are the currents that we have here. All right, now it could be that in some cases these currents actually give us certain errors in our circuit design. Just like the DC offset caused problems in previous stages. So let's look at a couple of cases and see what's the consequence of having these currents. By the way, if you have a CMOS op-amp, then these currents are extremely small and usually not troublesome. But for bipolar op-amps, they are more pronounced. All right, so let's go and look at the effect of these bias currents on, let's see, what did I do here? On the non-inverting amplifier. So we draw a non-inverting amplifier like this. R2, R1, plus, minus. Okay, so we have V in here, and V out here. And let's say V in is an ideal voltage source for now. So that's an ideal voltage source coming to the non-inverting input. And now we have to add these two currents. So we add a current source here, IB1, and another current source here, IB2. And we are wondering what kind of error we will get at this output as a result of IB1 and IB2. All right, well, so first IB1. IB1 flows entirely through this voltage source, and this voltage is undisturbed because this voltage is given by this voltage source. The voltage source, an ideal voltage source, imposes a voltage regardless of what's going on. So IB1 has no role in this voltage. We don't see its effect anywhere. Now, if that's a good thing or a bad thing, we don't know, but that's what happens. All right, so let's focus on IB2. IB2 needs to flow from this node. So it has to come from somewhere. Let's find the candidates for that. And to analyze this effect, I will assume that V in is 0. Again, I'm using superposition. So let's say V in is 0, meaning that we just short this to ground. And now we're looking for the effect of IB2 at the output. Okay, well, there are 3 wires connected to this node. One is the input of the op-amp, which presumably doesn't draw any more current because we already included that current source here. So there's no more current here. Okay, so nothing there. So there are only 2 possibilities. Some current through R1, some current through R2 to add up to give us IB2. Okay, but again, remember, if the op-amp has a high gain and this voltage is 0, then this voltage is also close to 0. Going back to the fundamental property. Okay, so if this voltage close to 0, it means that R1 has 0 on this side and approximately 0 on this side. So the current through R1 is also 0. So this current is approximately equal to 0. That means that there is only one path for IB2 to flow from, and that's just R2. So IB2, for the most part, has to flow through R2, like so. Okay, that generates a voltage of IB2 times R2 from here to here. And this voltage is close to 0. So V out, which is this voltage plus this voltage, will be approximately equal to IB2 times R2. So V out is equal to IB2 times R2 approximately, since the voltage across R1 is very small, because this voltage is approximately equal to this voltage, which we set to 0. All right, so that's the amount of error we get at the output. The output voltage has a DC in it, and that DC is equal to this bias current of the op-amp multiplied by the feedback resistor, R2. The other resistor doesn't play much role in this behavior. All right, now it turns out that there's a quick fix for this so that this error is removed. So what I'm thinking is this. I have a certain amount of voltage here, IB2 times R2. So what if I try to come from outside and add a little voltage source here? I know that this voltage source will be amplified by some factor that comes out. And if I pick the polarities right, maybe this voltage source, after amplification, is exactly minus this, so they cancel each other and the output is 0. So what I'm thinking is I can place a voltage source here. But now what do? I can't really buy a battery and put it there, so I have to figure out how I can create such a voltage. And there's a very simple way. So let me show you how that is done. So let's go ahead and do this. We redraw the circuit, and this time, this is what we do. We still have all of that stuff, R1, R2, positive, negative, V out. I'm trying to generate a voltage in series with this input so as to cancel the output, so as to null the output. Okay, so what I will do is I place two resistors here in parallel in series with the input. And I pick one to be R1, the other to be R2. And this will be the main input. And I claim that in the presence of IB1 and IB2, the output now is clean. It has no DC. Assuming that, of course, IB1 and IB2 are equal, which is a reasonable approximation. So let's draw IB1 and IB2 and look at their effect and see what happens. So IB1 flows from one input of the op-amp to ground. I have to draw it way over here. That was the model that we developed. And then IB2 from the other input. So that's IB2. And to see if the output has any DC or not, we'll use superposition, meaning we set the input to 0. So the input is 0. And we are curious to see if V out is clean. Okay. Well, how much is the voltage at this node? That voltage is IB1 times the parallel combination of these resistors. And it's negative because this side is 0, this side is some voltage, right? The current is flowing this way. So the voltage at this node is equal to IB1 times R1 in parallel with R2, and then a negative sign because the current is flowing this way. That's the voltage that we have here. how much output voltage do I get as a result of this voltage? I can use superposition again, meaning that I don't have to worry about this guy, and I measure the output voltage just resulting from IB1. Now from here to the output, I have a non-inverting amplifier, right? That's a non-inverting amplifier. So the voltage that I have produced here is multiplied by 1 plus R2 over R1. So I can say that V out is equal to the input voltage minus IB1 R1 in parallel with R2 minus IB1 R1 in parallel with R2 times the gain of the amplifier from here to here, which is 1 plus R2 over R1. This is the amount of voltage that we generate at the output of the amplifier only due to IB1 flowing through the parallel combination of R1 and R2. Now, let's remember that IB2 has its own effect, again using superposition. And the effect of IB2 at the output is the same as before. It's this much. Because with IB1 set to 0, having these resistors here doesn't change the gain of the circuit. Doesn't change anything as far as IB2 is concerned. So if we use superposition for IB1, we get this. If we use superposition for IB2, we get this. And we have to add these algebraically. So we have plus IB2 R2. This is the total output voltage of the circuit when we include both IB1 and IB2. Is this 0? Yes. So what you need to do is, this is R1, R2 over R1 plus R2. And this is R1 plus R2 over R1. So these cancel, and minus IB1 and IB2 are the same, so we end up with 0. So that's great. That's a very nice and simple fix that we use in conjunction with bipolar op-amps because we are worried about the effect of these current sources, these bias currents. All right, let's add a page. And let's look at the effect of these things on the behavior of the integrator as well. So let's consider the effect of these bias currents, input bias currents on the integrator. So input bias currents in integrator. So we're wondering what they do here. Okay, so no problem. We'll draw the circuit like this. That's our integrator. We have a feedback capacitor, C1. We have the out. Then we have a bias current from here to ground, which we call IB1. Another bias current from here to ground, which we call IB2. And this is connected to ground, this is connected to the input. And we are wondering if these bias currents cause any problems in this integrator design. Okay, well, this point is fine because IB2 just has to flow from ground, nothing here. This voltage is 0. But this voltage probably does something. Again, to study the effect of IB1, let's use superposition and set V in to 0. So we set V in to 0. And we have to trace IB1 through the circuit and see what it does. If the gain of the op-amp is high, this is a virtual ground. So this voltage is close to 0. If this voltage is close to 0, this current is close to 0. So IB1 cannot flow through R1. It has to flow through C1. All right, so this is what we have. IB1 is flowing through C1. C1 is integrating that current because we know that the voltage across the capacitor is the integral of the current through the capacitor. So C1 continues to integrate this current. This side is 0, and this side keeps going up, so the out keeps going up. Very similar to the effect of the DC offsets that we saw before. So what we see here is that V out also grows with time like this, and we can express it as 1 over C1 times this current times T. So that's the equation for that waveform. And it will go up until the op amp saturates, and then we're stuck. Okay? All right, so the integrator fails for two reasons. One is integration of its DC offset voltage, and the other is the integration of its bias current, input bias current. Okay, so how do we alleviate this situation? Well, a partial remedy is this. A partial remedy is to try to, of course, if that we add that resistor there, that resistor looks like this. Remember that resistor that we put here? That's really the only reliable solution that ensures that the circuit does not saturate. It forces any currents that we need to draw from here to flow from R2, not from C1. But we can also try to add a resistor here equal to R1 so that IB2 flows through this R1 and generates a voltage. And the hope is that this voltage and the Thevenin voltage of these two cancel each other, because I can replace this by a Thevenin as well. So if I replace them by Thevenin, this is what I get. I get R1 IB1 R1. That's for these two. And then this goes to the input of the op amp. And then here I also have same thing. I have IB2 times R1, IB2 times R1, but with a negative sign. And actually this is also negative. And then we have something like this. So what we are thinking is that because these two voltages are equal, the integrator doesn't see any difference, so it doesn't integrate. So yes, we could try to do that, and usually we do that with bipolar op amps. But keep in mind that if there's a slight difference between IB1 and IB2, we still integrate. So the only reliable solution is to use this resistor. But to alleviate the effects of the input bias currents, we also practice this method of inserting a resistor in series with a non-inverting input of the op amp before we connect it to ground. Very well. Let's talk about the speed limitations of op amps as the last type of imperfection in op amps. So we'll look at speed limitations. Well, remember that when we looked at the 741 specifications, we saw that the bandwidth of the op amp, when you buy it, is the 3 dB bandwidth is something like 1.5 megahertz, 2 megahertz, something in that range. So, but its gain is very high. It has a gain of, let's say, 100,000. So the question is, what type of speeds, what type of frequencies can I run this circuit at before it becomes useless? So to see that better, let's go back to the 741 example and try to roughly plot its frequency response, just the op amp by itself. So here's the op amp, and here's the 741. And for example, we have grounded the inverting input, apply something here, measure something here, and plot this frequency response. So if you want to call this frequency response H, the magnitude of H is like this. At very low frequencies, we have a huge gain, 100,000, right? So this gain here is 100,000. And this gain as a function of frequency holds up to about 1.5 megahertz, maybe 2 megahertz. So it goes up like this, and the 3 dB bandwidth is about, let's say, 2 megahertz. And then past that point, it starts falling. Okay. All right, so this is the general behavior of the op-amp. And we might try to approximate this by a first-order system, just like a simple RC. We will call this F0. This is the 3 dB bandwidth of the op-amp. And if we want to make a first-order system from it, we will write it like this. We'll say H of S for this op-amp from here to here is equal to A0 over 1 plus S over omega 0. Omega 0 is just 2 pi F0. We need that because S itself has 2 pi. And then A0 is this factor of 100,000. This makes sense, right? If S, the frequency of operation, is very low, we have a gain of A0. And then as this goes up, you remember that we take the magnitude of this from like Bode plots, and we see that it falls. Okay, so if we can model the op-amp by a first-order system like this, meaning this box is actually like this, not just A0, then we have to go back to every circuit that we studied before, and wherever we see A0, we have to replace it by A0 1 over 1 plus S over omega 0, and let's see what happens. We had the non-inverting amplifier, the inverting amplifier, the buffer, the integrator, differentiator, all of those things, right? So for all of those, we have to go back and re-examine the results, knowing that omega 0 is not infinity. This eventually rolls off. Okay, so just as an example, let's go ahead and repeat the analysis of the non-inverting amplifier with this type of model for the op-amp. All right, so here's the non-inverting amplifier. R2, R1, V in, and V out. So not only are we not assuming that A0 is infinite, so A0 is not infinite, it's small, moderate, we are also assuming that there's a frequency dependence. So what goes in here is this transfer function. Okay, so now we need to do the calculations. Now it's not that hard, actually. What we do is we look back to the equation we had before and simply replace A0 with A0 over 1 plus S over omega 0. So this is what we get. V out over V in of S, that's the transfer function from here to here, is equal to A0 over 1 plus S over omega 0. And then we have 1 plus A0 over 1 plus S over omega 0, R2 over R1 plus R2. So that's what we get when we go back to our equations and make that replacement. All right, so this equation is interesting, and we can manipulate it a little to make it somewhat more intuitive. Let me just check something here. If this goes to infinity, we have R1 plus R2 over R2, so that's R1 over R2. So actually this should be R1 here, not R2. Okay, all right, so let's play with this a little. I will write it like this. I will say V out over V in of S is equal to, let's go ahead and multiply by 1 plus S over omega 0, both the numerator and the denominator. So we have A0, then we have S over omega 0 plus 1 plus A0 R1 over R1 plus R2. So that's the transfer function of the overall amplifier, the closed loop gain or transfer function of the circuit. Okay, so let's compare what we got for this overall amplifier with what we had for the op-amp itself in terms of frequency response. So let me change the color of my pen and we'll see what we get. Alright, so for the op-amp itself, with one pole, we saw that the 3 dB bandwidth is given by the pole frequency, omega 0. And to find the pole frequency, we set the denominator to 0, right? And that gives us S equals minus omega 0. And that's how we find the 3 dB bandwidth. It comes here, starts rolling off. Okay, now let's go back to that circuit. And first, assume the frequency is very low and see how much gain we get at low frequencies. Here we had 100,000, A0. Here, if S is very small, we get this. So let's just write it out. So this is what we have. The gain is lower. The gain is now A0 over 1 plus A0, R1 over R1 plus R2. So that's the gain that we have. Obviously the gain is smaller. I'm building an amplifier with a moderate gain, a gain of 10 or 20 or something, not a gain of 100,000. So obviously the gain of this closed loop circuit at low frequencies is quite lower than the gain of the op-amp, the open loop gain of the op-amp itself. All right, now, where is this roll-off point? Where does this begin to roll off? That's a very important result. Well, to do that, to find this roll-off point, I have to find the 3 dB bandwidth of the circuit, the pole frequency of the circuit. This circuit still has a single pole because this S has a power of 1. And to find the pole, we set the denominator to 0. So we see that the pole frequency of the closed loop amplifier, including everything, is this whole thing times omega 0 with a negative sign. So it's 1 plus A0 R1 over R1 plus R2 times omega 0. So now we see an interesting difference between the op-amp itself, which we call the open loop circuit, and this closed loop amplifier. We see that the pole frequency, the 3 dB bandwidth, has changed. It used to be F0 or omega 0, there's a factor of 2 pi difference, and now it's not. It's that factor, that multiplied by a pretty large number. Right? So the bandwidth of the circuit has been extended to not just omega 0 or not just F0, but with this factor multiplied by it. So now it's way out here. And this value is given by all of that. So it's 1 plus A0 R1 over R1 plus R2 times F0. I use F0 instead of omega 0 because this is the F axis. So this comes all the way here before it starts rolling off. And in fact, what happens is that these both meet farther up and they go down together. Oh, sorry, they actually meet right here and go down together. So I have to clean this up a little to make sure that you have a correct plot. So for this guy, we have something like this. And then for this guy, we have something like this. So the beautiful result that comes out of this analysis is the following. We reduced the gain of the circuit from 100,000 to 1 plus R2 over R1. We started with 100,000 and we got only this much after we applied these resistors and so forth. But the gain went down and the bandwidth increased. The bandwidth used to be F0, now it's F0 times the same factor. So the same factor by which the gain is reduced also increases the bandwidth. In other words, we are trading the gain for the bandwidth. We reduce the gain from 100,000 to, let's say, 10, and at the same time, we increase the bandwidth from, let's say, 2 megahertz by a huge amount. All right, so that's the beauty of this type of circuit. You can trade gain and speed for different amounts that you can see here. I should give you a cautionary note though. Let's say I reduce the gain from A0 100,000 to something like, for the closed loop, let's say 10. So the gain has come down by a factor of 10,000, right? Does it mean that the bandwidth goes from 2 megahertz up by a factor of 10,000? No, that is not true. Because what happens is that this roll-off eventually comes down to some finite amount, maybe 10 megahertz or something. So you cannot go past that regardless of what we do. But generally, so long as we're not too aggressive in this type of trading between the bandwidth and the gain, we can increase the bandwidth to some extent. All right, so that's one speed limitation that we saw here. And when you learn feedback, negative feedback, for example, in electronic circuits 2, then these things come into play more clearly and more effectively. The last effect that I want to show you, as far as op-amp imperfections are concerned, is what we call slew rate, and that's also related to speed. So let's talk about slew rate and see what that means. So slew rate. Well, if you take an op-amp like the 741 and you build some sort of circuit, an amplifier, and then you apply some inputs, you see something interesting happen. So here's how it goes. Let's take a very simple amplifier like this. V in, V out. And we come along and apply a step here. Very simple, right? You apply a step here, you should see a step here, amplified by some factor. Okay. So in the ideal case, this is what we should see. If the op-amp were ideal, you apply a step here, you get a step here. If the op-amp is not ideal, it has some sort of bandwidth limitation, then we apply a step here, we get an exponential here, just like any other first order system, like a simple RC filter, right? All right, so assume that this op-amp has a one-pole bandwidth limitation, but no other imperfection. All right, so in that case, this is what we should see. I will plot the input and then the output as a function of time. So I apply a step, I see an exponential. Okay, amplified with respect to the input. Then I keep increasing the height of the step. And what I'm hoping, let's change the color of the pen here. If I increase the height of the step, what should this exponential do? Well, it should go like this, right? So what's interesting is, if the op-amp has bandwidth limitation, according to first order system, but doesn't have any other imperfection, then as the step height increases at the input, this output has a slope that also increases. You see the slope and now the slope. All right, so if I increase this farther, then this also goes like this. Okay, but if we perform this experiment on a real op-amp, we see that it's not quite like that. Something strange happens. So let me draw these waveforms again, this time with a real op-amp, which is not just limited by this type of one-pole response, but by some other mechanism as well. So let's change the color of our pen and see what we can do here. Okay, so we have V in, a step, and then V out, an exponential. So if V in is a small step, no problem, similar to before, you have an exponential. And now we come along and increase the step height like before. So we give it another new step, and we see that it did this. And now we keep increasing the step height at the input. So we go to a higher step size. And what we see is that beyond a certain point, as the input step height increases, this slope doesn't increase anymore. It actually looks like a straight line, and then it settles like that. So if I give it even a higher step, it just goes like this and then settles like that. So this slope fails to scale like before. You see here, with only bandwidth limitation and nothing else, the exponential would have a higher slope depending on the height of the step at the input. But in this case, initially yes, but then at some point this slope remains constant. It is as if a constant current is charging a constant capacitance, right? We know that in that case we get a ramp. So it looks like a ramp for a while before it becomes more or less like an exponential. So this slope, which we eventually reach and we cannot surpass, is called the slew rate of the op-amp. Slew rate of the op-amp, and this effect is called slewing, meaning that the op-amp cannot go faster than this. It has to go on this tangential line, if you will. All right, so in this regime right here, the op-amp actually looks like this. We have an op-amp in here, and there is a current source charging a capacitance. So from here to here in this case, or from here to here in this case, we have this type of model inside the op-amp. Something is going on like that. And it looks like a constant current charging a capacitor, and that gives rise to a ramp. So for every op-amp that we buy, we have a certain slew rate. And for the 741, I don't remember, it's like 1 volt per microsecond or something, meaning that this change cannot be faster than 1 volt per microsecond. And for different op-amps, we get different types of slew rates. And this is an important concept because, first of all, you can see that it limits the speed, right? We were expecting that this would go like that. You see, it would go like that, keep going faster and faster. But it doesn't. At some point, it cannot go faster. So it limits the speed of the op-amp. And it has other interesting repercussions. For example, if the op-amp is to produce a sinusoid at its output, a large sinusoid, a high amplitude sinusoid, then something happens. So ideally, the op-amp must generate a nice sinusoid here. And let's say this is a large swing. You know, in the case of 741, this might be plus minus 5 volts or something like that, right? Okay, but what happens is that in the presence of the slew rate, we no longer have a sinusoid. So right around here, we are asking the output of the op-amp to change quickly. So we're asking the output of op-amp to change quickly across a large value. And the op-amp says, I cannot. I have only this much slew rate. So what happens around here is that the output of the op-amp goes like this, because it cannot keep up with the speed that we want. Similarly, around here, we say you have to go this fast. The op-amp says, I cannot do that. I have only this much current charging that much capacitance. So it has to go more slowly, like so. Well, sorry, actually this is the wrong waveform. Let me correct it here. So we have the original waveform like so, and the new waveform will be like this. So it says I cannot keep up with this, so I have to go more slowly, and then it goes like that. So what you see is that the output sinusoid is distorted because it was supposed to go sinusoidally here, but instead it decided to go as a ramp. And that's a distortion that can be quite objectionable depending on what we're trying to do. So the slew rate is another important effect in op-amps that we must always keep in mind when we are dealing with various speeds, etc. All right, this concludes this lecture, and this lecture concludes this series. Thank you for joining me for 45 lectures. I'll look for other series that I will create in the future, including problem-solving strategies for electronic circuits 1, also electronic circuits 2 and problem solving strategies for electronic circuits 2 and other types of subjects that will come up in the future.